So hello everyone, welcome to week 9 of these tutorial sessions. So we'll wait for a few minutes so that more people may join. So in the meantime, if you have any questions for the last week, you can ask your questions or you can type it in the chat.
So I have a general query. Uh, like
Yes.
this NPTEL exam, it's all objective.
Yeah, so the questions will mostly be of the form that you have seen in the assignments. Yeah, it will
Okay.
be objective, maybe one or two numerical type questions may be there, but yeah.
Okay. And like it's multiple select or like
So that will depend on, so I'm not sure about that because that will be set by the NPTEL team and the professors. So we are not involved in that, so I cannot really say about that.
okay. Actually, from NPTEL team, anyone will be taking any session like for such queries
So you
before the
can
exam.
drop a mail to the NPTEL team. Maybe they will reply to your questions, or they may, you have access to the Google group, right? So you can post the questions there and someone from MTTL team will reply to you, because we
Okay.
are not really involved in conducting the exam, so I cannot say anything.
Okay.
So okay, let me join from my iPad and then we can start. Okay, so this week the topics that were covered were mostly how to represent words as vectors, right? So till now, you have been looking at a neural network as if you get some input as input X, and you use that input to do a feed forward across the network, compute the loss, and do a back propagation and update the parameters, right? So in all of these, your assumption was that you had your matrix or you had your input as a vector. So the general framework that we have discussed till now is that you have some d-dimensional vector x, you pass x to the neural network and you get some prediction, right? And then you back propagate it and learn the weights. But so this is the first lecture where we actually look at how do you handle actual data, right? So till now you just assume that you have some d-dimensional vector and then you do your downstream tasks on this multi-dimension vector. But what if when we are talking about actual data, there can be a variety of this, right? So you can have images, you can have text, or you can have different signals like audio signals or speech signals. So you must, so as we saw, the neural network expects some vector type of input, right? Here it expects that you have a vector, and then the rest of the task is easy. So how do you go to this vector? So in this lecture, in this last week's lecture, the the data type that we assume was of textual data. We are given some sentence, or we are given a word, and then we have to act upon that word and do maybe classification or regression, which are the commonly used tasks. So the most basic the most basic vectorial representation that we can have is the one hot representation. So again, if you think this the topic that I'm explaining is easy and you want to understand a more different topic, you can just go ahead. But since you're not uh, you don't have any questions, I will just cover the topics that were covered that were shown in this week's lecture. Okay, so the most basic thing is the one hot representation. So the example that was given was that you have a couple of sentences, and then using these sentences, you look at all the words that are present in these sentences, and those now form your vocabulary. So basically, you have a sentence, say, I have a dog. His name is, say, Harry. Uh, his, suppose you have these three sentences. So when I say vocabulary, I look at all the words that are present in this sentence, right? So how many words are there? We have all unique words. So 1, 2, 3, 4, 5, 6, 7, 8. So his has already been counted. So 9. His has already been counted, and black 10. So you have 10 words in this vocabulary. So these are I, have, a, and so on up to black. So here my vocabulary size is 10, right? So now what we do is, for each word, we just say whether, for each word we have a 10-dimensional vector, and we just say that whether that word is present or absent. So if I say that what I have, if I take the word dog, right? So dog will be at the 1, 2, 3, 4 at the location 4. So you have 1 at location 4, and all of these will be zeros. So you have a vector of this one. So this vector represents dog. So before going further, so what will you do is that we have this vector x. Now you can use this x, which is the vector of this one, and you can pass it to a neural network, and you compute whatever task that you want to compute. So this is a very naive way of computing vector representations of words. So the problem here is that this V can be very large, right? So suppose uh, you are training a model and your data set is a collection of all the text that is available on the internet, right? So that means there are thousands, millions of websites, and there are almost billions and trillions of words there. So if you want to compute a vocabulary of all of these words, so this will be a very large, like this size of V will be very large, right? Because you have to look at all the websites and all the sentences in this website. So then this model becomes very costly. It becomes very infeasible. You do not want so large models. So another problem is that, as it was discussed in the class, this type of representation does not really say anything about your closeness. So suppose mm, I have a representation for dog, and yeah, I'll use the same example. I have a representation for cat. So, and also I have a representation for say um, humans. So, so in the ideal sense, what do you want? You want that the characteristics of dog and characteristics of cat are similar, right? So they have four legs, they have a tail, and so on. So if you are doing some neural network based training or some task, so you wanted the dog and cat words should uh, be treated similarly. So suppose you have a question answering task, right? And then uh, suppose our question is what is given example of a pet. So as an example of a pet, you can either give a cat or you can give a dog. So why is that? Because why? Because we know that uh, s- when we see the word pet, there are only a handful of pets that humans keep. So the set of pets may be dogs, cats, cows, and so on. So so that means the dogs and cats must be similar in some sense. So dogs and cats must be similar in the sense that they are both of them are a type of animal known as pet. So in order to explain or in order to capture this similarity, this one hot representation is it does not say anything actually, because say my dog is as given here, and suppose I have a different vocabulary, and where my cat is say cat is given something like this 00001. Suppose my cat is like this, and whenever you are talking about similarity, we wanted the dot product is similar. That means suppose I have a vector in this direction, right? And I have a different vector in this direction. So suppose I say that this is my vector u, this is my vector v, and I have a third vector in this direction. So a quick question to you. If I say what is the given u, which vector is most similar to u? Is it v or is it w? Which is the most similar vector to u, v or w? So you can just unmute yourself, and because this understanding is needed for understanding what we are trying to do here. So the question is which,
He
like,
is closer to user.
yeah, V is closer, right? Right.
We will calculate
Oh,
cosine angle for this.
right.
Cosine similarity.
Correct. Mm. So that means if two objects V and U are similar, their vectors should also be close to each other, right? So that means if I do the cosine similarity of U transpose phi, this should be reasonably high, right? Because if two vectors are aligned together, if two vectors are close, their similarity or their dot product is high. But now, if we have these two vectors of dog and cat, so we want dogs and cats in a certain vocabulary to be same. But let us see what happens. So we have, if I do say, so this is my vector say u, and this is my vector say v. So if I do v transpose u in this case, what do I get? So here 0, 0. I don't know, it should be a 10 dimension vector, I guess. And I have another one here. So what is the result of this dot product? Anyone? So I'm taking the dot product of v transpose u in this case. What is the dot product that we get here?
We will get zero only. Sir.
Yeah. So all of you get this, right? This is just simply element by element multiplication and then addition. So you get 0. So now we have a problem, right? Because we wanted dogs and cats to be similar. So we wanted V transpose U to be high. And by high, we mean that it should be close to 1, say. But now we are getting that this quantity is 0, which is not correct, right? So this one hot representation does not exactly, even though it is very easy to implement, it does not say anything interesting about the data that we have. So now we look at a different way of representing these words that we have. So one of the techniques that was discussed in the class was that of a co-occurrence matrix. So co-occurrence matrix basically tells us that suppose you are given a group of sentences and two words occur together a few times, so that means those two words are related. So if I say we eat at a restaurant, the restaurant has chairs and something something. So, by common experience, we know that this word eat and this word restaurant must be related to each other, because whenever we talk about eating, we mean we are eating at a restaurant, right? So, this is structured by the co-occurrence matrix. So, what co-occurrence matrix does is that given your vocabulary, suppose you have a vocabulary P of size P. So now, so suppose let's say your vocabulary is, so your first word is V1, second word is V2, and so on, and you have V many words. So now you create a matrix where your number of rows is your number of words. So you have V1, V2, V3, and V3. And your number of columns is also your number of words. V2, P3. And now what you do is for each word, say for each word, you look at how many times that word occurs with each of the remaining words. Say suppose I take the word V1 here. So suppose I take the word restaurant here. Suppose I have a few more words. The restaurant is green in color. So suppose my word V1 is restaurant. So suppose this is restaurant, and suppose V3 is eat, and suppose I have a V4 here, and V4 is the. So I want to see my vocabulary will have all of these words that are given in these three sentences. And now let me see how many times restaurant occurs with eat. So we see that in all of these restaurant occurs with eat only once, right? So this will have a one here. And then again we see how many times does restaurant occur with the word ta. So you can see that it appears two times here. So, and we'll also have something for we have a and so on. So we only want to look at the closest uh, context. So by closest context we mean, so given some word, say I have some word w, and I create a window of size say 2. So that means I want to see how which word appears in the next two words of w, or which words appear in the previous two words of w. So this is a context window that we have. Right. So which word appears within two times or two places of w, either before w or after w. So here we see that okay, so the restaurant is, this example is a bit wrong. So suppose let me say my context window here was the size of 4, and by 4 I mean 4 words before w and 4 words after w. So then if we keep a context of 4, then we see that restaurant will have eat once and it will have da two times. But we also have a we here, so we does not appear in a window of 4 from the word restaurant. So we'll not have anything here. So we'll get for, so now earlier our vector was of this form, either zeros or 1. So now our vectors will be of this form, of uh, how many times it co-occurred with other words, and zeros in all the rest. So if I talk about our restaurant, it will be something like this: 0, 0, 1, 2, 0, 0, 0, 0. So again, what is the length of this vector? Anyone? What is the length of this?
6.
Come again? I did not hear you. So we're creating a matrix of all the words here and all the words here, right? So for each word, what will be the length of this vector? So it will be v itself, right? This will be v, right? Because you're looking at all the words. You're looking at the co-occurrence of some word with all of the words. So this will again be v. Now let us see one thing. So you see that we know that restaurants should be correlated or co-occur with the word eat, but restaurant does not exactly have any reason to be that important for the word da, or da is not that important for restaurant because da can be anything, right? This da can is a very common word in sentences, and it can be uh, so it can give a lot of extra information that we don't need. So words like da, at, a. So these are very common words, and we don't get anything new out of these words, right? So these are called stop words. So stop words are, for example, da, that, a, is, of, and so on. Like these are not these type of words do not give us any new information, so we are not bothered about these words. So we can remove these words. So what is the effect of removing these words is that this length of the context length of each of the representations it decreases a bit, but not that much because there can be only a certain number of stop words. So this is just you can say that you can do given the data set you can just remove these stop words because these are not so important, and create a vocabulary out of the remaining words, and then you will get something. You get your representations. Okay. So then there is another concept that is shown is the concept of PMI. So, uh, so pointwise. So this is basically called pointwise mutual information. So it basically gives you a score of uh, how close or how correlated your words are. So, so if you look at the slides, okay, I think in slide number 11 they have given the example or the formula. So this is basically log of the probability of context given word and probability of context. Right? So C is basically says that it says that you have some count of WC. So this count is derived from the this co-occurrence matrix uh, that we constructed. So this is some co-occurrence matrix that you have, and this gives us this is basically giving us count of phi1 comma phi4. So you put that count here. Then you have count of C. So count of C says how many times C occurs, and then count of W times N. So in a sense, it says that if if some context word appears a lot of time, if some W or some word W appears a lot of time, so this product will be large, right? Because these two are large numbers, and if they occur together a lot of time, so this quantity will be high, right? Because this is high, and even this is high, so this quantity will be large. But if this is high and this is high, say C occurs 100 times, W occurs 100 times, but they never occur together. So this suppose this thing becomes 0, then you have a low PMI. So PMI is basically it shows it gives you a way of uh, how do you characterize that two words occur together? How do you measure how much closeness these two words have? If PMI is high, then that means those two words are correlated. They occur a lot together. If PMI is low or zero, that means they never occur together. So that is what we use. So this is basically substituting for the co-occurrence matrix. So earlier in the co-occurrence matrix, you just have the counts. So now instead of the counts, you have this PMI scores that you compute. So any question on that? Okay, and so there is another. So because this is a log, so you can also get negative values. Okay, you can also get negative values. So that is why there is this adaptation called positive PMI, which says if your PMI is positive, then keep it. If your PMI is negative, just set it to be zero. So again, even if we do this, we do co-occurrence matrix, or we substitute the counts in the co-occurrence matrix with these PMI scores. Even then, these vectors are very large, right? We have each of these vectors are of size p, which is very large, and we want to reduce dimensionality of this. So I think last 2 weeks back or 3 weeks back, we covered dimension reduction techniques. So we covered PCA, we have covered SVD, right? And so this is where those things come again. So because we have to reduce this dimensionality, so maybe we have say phi is of the order of 10 to the power 6, and I say no, I don't want to look at all of these because this is very costly. I just want phi to be of the order of say 200. So what I'll do is I'll basically do a SVT of this matrix. So suppose my co-occurrence matrix, suppose it is X, right? And now X is very large. So suppose it is 10 to the power 6 times 10 to the power 6. So it has around 10 to the 12 entries, and that is very large. We don't want to deal with such large matrices. So what we do is we compute the SVD of this. So if we do an SVD of X, it gives us these three matrices. You have U, you have sigma, and you have P transpose. So I hope SVD is clear with you because it was covered in an earlier class. So we have k columns of U, we have k singular values, and we have k rows of pi transpose. So using this, what we can do is, so now there is a thing in SVD. So suppose you have k non-zero singular values. So singular values are always positive or zero. So you have k non-zero singular values. So we say that the rank of the matrix is k. But if we want to have a lower dimensional representation, so suppose my rank of X, which is my co-occurrence matrix, is say very large, say 10,000, and I want lower dimensional representation. Say I want rank of, say, some approximation x tilde to be, say, 100. So what I will do is that for x I will have this use sigma p transpose, and then I will just take the first 100 columns of this. I will take the first 100 singular values of this, and I'll take the first 100 rows of vi transpose, and then using only these 100 singular values, we'll get some x tilde whose rank of x tilde is 100. So this is just a low rank approximation of x. So how is this helpful, right? So now, so suppose for convenience we are using this. Okay. Oh, is this visible now? Okay.
Yes, sir.
Mhm. So if it was not visible, I'll repeat. So you are given some co-occurrence matrix X, which is of rank say 10,000, and now you want a approximation of X, which is of rank say 100. So what you do is you do a SVD of X, and now we just take the first 100 columns of uh, U, say the first 100 columns. You take the first 100 singular values of sigma, and you take the first 100 rows of phi transpose, and then using this you will get some x tilde whose rank is 100. So this is called rank 100 or rank k approximation. So how is this helpful in our case? Let us see. So suppose, so we earlier we looked at this positive PMI, right? You have non-zero PMI entries in your co-occurrence matrix. So suppose we are given that. Okay. So suppose we are given this XPPMI, and I can write this as, so suppose it is M cross N. It is an M cross N matrix. So suppose I can write this as I do an SVD of this, and then I get something like this. So if you remember, so yeah, let us take a detour. Let us go back to when we were discussing autoencoders. So what were we doing in autoencoders? We have some vector x. You want to learn a representation of x. So you pass it through an autoencoder. You get some latent representation. And using the decoder, you want to reconstruct x, right? So if we look at this latent information, so this was your latent representation. So we wanted that the latent representation that we learned via this autoencoder, it captures some important information about your data set. So I gave an example of an image of a cat. So this latent representation should learn that cats will have two eyes, it will have a nose, it will have a mouth, it will have pointy ears, right? So those representation are called hidden representations, because those representation are not actually given to the network. The network learns those representations, so those are termed as latent representations. So now when we do this SVD, it also captures the latent representations of the vectors. So by that I mean, so in our case, what latent representation did we want? We wanted that if two vectors, say dog and cat, are similar, then they should be close to each other, right? So that is in the representation. We wanted that the vector which represents dog and the vector which represents cat should be close to each other. Or in this example, we wanted the vector which represents restaurant and the vector which represents eat should be close to each other, right? So SVD helps to capture this information as well. We did not have that provision in one hot encoder, but sorry, one hot representations. But now when we're doing an SVD of the say PPMI matrix, we have that information. So how do we get that? So again, let us look at the form of SVD. So we have X, which is U1 to UK, sigma 1 to sigma K, and V1 to VK. And if we do a bit of manipulation, so we can actually write it as sigma 1 V1 P1 transpose plus you can actually write this like this. And suppose now I want a rank 1 approximation, so I will just if I want a rank 1 approximation, I'll just say that this is the rank 1 approximation. If I
Can
want a rank,
you explain latent representation again?
okay, sure. So by latent representation, I mean, so if you remember autoencoders, so we were given some input vector x, we passed it to the encoder. Okay, we passed it through the encoder. We got some vector h here, and then once we get this vector x, we passed it to the decoder so that using h you are able to learn x or you are able to reconstruct x again, right? So that means h is a representation of x in some space. So suppose your input x was a say 800 dimensional vector, right? So let me give an example. So your input is an 800 dimensional vector. You pass it to a neural network. So here you have a 50 dimensional vector, and again you want to reconstruct the same edge, so you have an 800 dimensional vector here. So that means this 50 dimensional vector that we have here, it should be able to represent the vector x, right? So earlier x was in 800 dimension, now it should be able to represent this in the 50 dimension space as well. So it learns, so
Yes.
right. So it will try to learn something about the data which will help it, right? So it will learn some information that say for the example of cat, it has two pointy ears, it has two eyes and so on. So these representation are not explicitly given during the input. This is learned by the network, and it is hidden from the input that we give. So that is why it is called the latent representation or hidden representation.
Yeah, thank you.
Okay. So this, so it was found that this SVD, when you do an SVD of this PPMI matrix, it is also able to capture this latent information between the words. So that was not possible for dog and cat, where we saw using this example that since dog and cat are similar, they should have high dot product. But using one hot encoders, one hot encodings, we actually get dot product of 0, which is clearly not what we want. Okay. So So using this SVD, what we do is now given some PPMI matrix. So PPMI, for this you just first of all you need to compute the counts of each of these elements and the counts of their co-occurrences, and then you calculate the positive PMI, and then you get back this XPPMI matrix. Using this matrix, what you do an SVD of XPPMI, and then you construct a low rank approximation of this. And say you get something, say X tilde here. And now you use the rows of X tilde. So now you want to see the similarity, right? So what is, one second. So now we wanted to see the similarity between two words. Just suppose in some vocabulary you have some representation for dog and some representation for cat. Suppose this was a V1, this was a V2. And now we want to check what is the similarity of dog and cat. So we'll just do a V1 transpose V2. So if we're doing this at vector level, you can write it as V1 transpose V2 or V1 V2 transpose, depending on how your matrix looks like. So actually, yeah, because your V1 is already a row vector, so this should be a column vector, so it should be V1 V2 transpose. Because you want something like this. So this is your V1 and this is your V2 transpose. So if we want to create a similarity matrix, say we want to look at the similarity of each word to all the other words. Say your co-occurrence matrix has V1, V2 and V100, say, and V1, V2, V100. And I want to create this, what is the similarity of this V1 and V1, what is the similarity of V1, V2, what is the similarity of V1, V3, and so on up to this. And we want to do this similarity for each of these. So we can simply compute this thing called X tilde transpose. So that will basically give us a similarity of all pairs of words that we have. Page number 82. Okay, I'm not able to see the page numbers. Is it this one? Okay, this one. Sure. So now how do you leverage these things? So earlier you had these large mod of three dimensional vectors, and those were very large. So that is why you came to this co-occurrence matrix, and now you compute a low rank approximation of your co-occurrence matrix using SVD. But how do you use this to, so finally what do you want? We want a representation of dog, we want a representation of cat, right? Or each of these words. How do you get there? So now if we look closely, what this was saying is that what is a semantic? So in if you're doing some related task, we should always understand what your data is trying to say or whatever your model is trying to say. So if I have a co-occurrence like this, so yeah, maybe okay, let me show it. So it says that given some word v1 in the context of say another word say v2, what is its score? So we are saying talking about PMI, right? Pointwise mutual information. It says what is the score of this say word v1 and v2, or given this word v1, in what context is this word occurring? So these are called the words, and these are said to be the context. By context, I mean in what context is just word occurring. So in this example, hmm, if I'm talking about the color green, so it is occurring in the context of restaurant, right? So if there is another sentence, the tree is green. So that means the green is word green is occurring in context of the word tree. So that is what we mean by context. Context basically says why is this word occurring in some sense. So this number of these columns that we have are it gives us the context in which your word is occurring. Right? So now, so let us look at this. So we have using SVD we compute x tilde, and now if we do x tilde transpose, we have the similarity of each word with each context, right? So this is our word and this is my context. What is the similarity of what is the score of this word with respect to this context? We have this. So now I can write this as say u sigma p transpose and transpose of this. So this basically says, so if you remember, I think the third or fourth lecture where we discussed orthogonal matrices. So what we said was, if two matrices, if some matrix X is orthogonal, that means X transpose X is I, the identity matrix. So when we're talking about singular value decomposition, these matrices are orthogonal. So this becomes I, and so we get something like this: sigma transpose U transpose. So that means I can write this as U sigma transpose. So now I am saying that when we are doing this SVT as a side, you have x equal to U sigma phi transpose, and suppose I say that this phi represents the representation of the context representations, and I say this U times sigma is gives us the word representations. Representations. So that means we XX transpose gives uh, the word representations. So which was written as W word in the lectures times the word representations transpose. So that means if once you do an SVD, you can use this product U sigma for representing your word. So you have words like dog, cat, monkey, human, and so on. You do an SVT of that matrix. So the representation of dog will be U times the matrix sigma, the first column of that matrix, U times. So for cat, it will be the second column of the matrix U times sigma, and so on. Is this clear? Okay. So, so the one issue that we have here is that you still have to compute this SVT, right? So SVT is actually a very complex operation. It requires almost qubit time, and also the size of our vectors are large. Mod of E can be very large, say 100,000 or so. So then people came up with ways of learning these representations. So right now we are just computing these representations based on whatever data that we have. Since this is a deep learning course, we want things that we can learn instead of just computing. Right? You give it some X, you give it some Y, and learn something about X using Y. So people also did the same thing and came up with a few learning-based methods. So one of the most popular one of them was the continuous backwards model and the word-to-vec model. So, uh, so in class we discussed about this task, right? The autocomplete or prediction, word prediction. So you must have seen this when you're using Google, right? You type one word and then it is not actually word prediction, but yeah, maybe in WhatsApp you are typing a message and then it shows you, it gives an option of what the next word could be. It gives you three options what the next word could be, right? So basically you can uh, so suppose I write the monkey is sleeping, uh, and I want to predict this word. So so some machine learning model should know that the monkey only eats a few things. It cannot, for example, say that uh, you have something like a mountain or something. So that is wrong, right? So it should, the probability that the model predicts mountain in this case is wrong, but it should be okay if it predicts banana or predicts apple, right? So that means given the sentence, you want to predict which one of this is most likely. So this is your traditional classical problem in machine learning. So, so suppose I give this as an input to a neural network model. I have a neural network here. I give this sentence as an input, right? And then it will tell me what is the next word. What is the next word that it has. So that is basically a classification problem. You have to classify which one of these what is the next word that you have. So quick question to you, what is the number of classes here? So in classification you read, right? So in binary classification you have two classes, either 0 or 1, or you have three class classification problem. But now you have to predict the word. What is the number of classes that you have? Do you get my question?
Three classes.
Uh, Not three class. Oh, okay. Okay. Don't look at this example. So I just showed this as an example. But in general, if you have a vocabulary of p words, so that means you will have p number of classes. because out of all of these you have to select only one, or you have to select the class with the highest probability. So suppose my vocabulary has say 100 items or 100 words, let's say. So that means I have a 100 class classification problem. But yeah, for the example that I showed, yeah, it is a 3 class classification problem. In general, it is uh, number or size of the vocabulary that you have. Okay. So if you remember the previous classes, we discussed the softmax function, right? So that means, suppose let us take an example of 3 class classification problem. So you have first class is the mountain, the second class is banana, the third class is apple. So once you do a softmax in the last layer of the neural network, it will give you a probability, right? So say it says the probability of mountain is 0.01. It says the probability of banana is 0.89, and probability of apple is say 0.1. So obviously, since banana has the highest probability, your machine will output that the monkey is eating a banana, right? So that is that probability distribution. That probability is given by this softmax layer that you had in the last layer of the neural network. Okay. So now we know what to do, but how do you make a neural network out of it? So you give some sentences input. You expect your network to give a word as output. How do you construct a neural network out of it? So now we know that for the neural network, our output layer is, we have a, this is our output layer. Output is of size of the vocabulary, right? Your input is some. Hmm. So for okay, so in the class for simplicity, we just took a context word, and let's say we don't have this word a here, and say that our context is eating, right? So we want that given eating, what should be the next word, right? Given eating, what is the next word? So now I have this representation of eating here. Suppose I have a one hot representation. So this is a 0, 0, 0, 1, 0, 0, 0, 0. So this is my one hot representation of eating. So this is the context that we have. This is the output that we have. And now simply we put some layer here, hidden layer here, say H, which is k dimensional. So this is 3 dimensional. This is also 3 dimensional. And now we have some k dimensional here, k dimensional layer, and now you have a neural network, right? So this is your input layer, this is your hidden layer, and this is your output layer. So now again, this looks similar to what we did for autoencoders, right? We have some input layer, some output layer, and we want to learn some representation here. And similarly, we want to do the same thing. We have some input representation. We have some prediction of the output, and using this, you want to learn a representation of your sentence or representation of your word. So the weight matrix, so because this we have to go from a v dimension space to k dimension space, you need the weight matrix. And because you are using a one-hot representation of the context, so this was marked as the W context matrix here. So again, quick question: what is the size of this matrix? You have to go from V space to K space. What is the size of this matrix? So this is just K cross V, right? And again, this was represented as W word. So to relate it to the SVD thing, so when you're talking about SVD, we are saying that each word in the PPMI matrix is represented by each row of this matrix U sigma. So now instead of explicitly giving what those things are, we're saying that those are represented by the rows of this W word matrix. So because the neural network will be optimized using say gradient descent, so the parameters of the neural network will be updated. So once we have learned all these parameters, the matrices that we get here, those can be used as representations of the words of each of the words. Because these words will try to capture the hidden representation which exists between the words. Is this process clear? So this W context and W word. So these are your learnable parameters. So that means these weights or these matrices will be updated whenever you are doing gradient descent. And this each row is a representation of the context, and here each word or each row is a representation of the word. So once we have this representation for each word, or from this, after training this model, so those representation can then be used for training the neural networks or whichever task you want. Okay. So this is a the setup is you get the setup, I hope, because now we have the context for this input. We know the size of the output, which is all possible uh, probability distribution over all possible words that can occur after seeing the looking at the context. And using this, we learn what are the representation of the words, what are the representation of the uh, context. So then we can just extract these learned representations that we have, and then use it as vector representation for the words in your data set. Now coming back to the last layer. So last layer was, as we discussed, so give me a minute, I have to connect my charger. So yeah, so now we come to the last layer that that we have. So here we saw that we need a probability distribution over all the possible words that may be predicted, right? So you need a probability distribution over length of v. So we have to compute the softmax for this layer. So if you look at softmax, what is softmax? Basically, given you have some mm, representation of the words, you take the ith entry of that, and then you sum over all of these entries. So if you look at this term, so this term you have to sum over all the v entries, right? Again, we come back to the same problem that you have a very large vocabulary of hundreds, thousands, billions, and then you have to compute a sum uh, over all of these quantities, or over all this length of this whole vector. So we want to do that a bit fast. We don't want to look at we don't want to get stuck in computing this. Okay. So again, before going into that, yeah, I forgot. So this is a classification problem that we have, and we're using the softmax distribution for this. So if you remember from previous classes, what type of loss function do we use for a classification problem? So for regression, we know that we use mean squared error. So mean squared error is basically difference of the prediction and the output and the square of those terms. So for classification, can anyone say what loss functions we are looking at? So we're looking at the cross entropy loss, right? So cross entropy basically you had this summation I yi log yi sort of thing. or y hat, and you have to maybe maximize this or minimize the negative of this. So in this case, your output is, your output, right? Your y, say when we are talking about, where did it go? We're talking about eating. You know that your output banana should be 1 and all others should be 0. So that means this should be 1 and all others have 0. So basically in this case, your loss function for the parameters is minus log of y yi hat, and your yi hat is the cross entropy that we, sorry, is the softmax distribution that we computed here. If you put it in this equation, you will get some nice form that we can train the neural network on. So basically, if you minimize this, right, you can train a neural network, because now you have a loss function, you have a objective that you want to minimize this, and then you have your input. So using this, you will be able to train this neural network, right? You train this neural network, and then once it is trained, you get this matrices W context and W word. And once you have these matrices, you can get back the representation of these words, and then you can use those word representations for whatever neural network task you want. So are there any doubts on this? Um, there are a lot of steps involved, but I hope the flow is clear. Or is there anything you want me to explain again?
Yes, no doubt.
Okay. Okay. So now we look at some computational issues. So because one main issue we had was this summation in the denominator term, right? Where we have to go and sum up all of these p entries, mod p entry, and we don't want to do that because that is costly. So three common ways are uh, were discussed in the class. Okay. So first one was negative sampling. Right? The first one was negative sampling. So now see, if you're summing over all of these keywords, you know that your word is uh, occurs uh, with some words. It does not occur with some words, right? That means, say, yeah, eating will occur with, say, banana or apple. Eating will not occur with mountain. So that means you know pairs of words which will occur together from your vocabulary. You will know pairs of words which do not occur together. So then you can form a set of positive samples and a set of negative samples. So for this, we form a set of positive samples, and we have a set of negative samples. So this contains all the pairs which occur together, say eat banana, eat apple, and so on. And here you have words which never occur together, say eat and maths will never occur together, and so on. So now we have this, I named this data set as D, and I named this as D prime. So instead of looking over all of these keywords, we only look at the words which are, or we look at the pairs which are in D and pairs which are in D prime. And then what we want is, if two words occur together, we want some score to be very high for this, and if two words do not occur together, we want their score to be very low for that. So uh, this is basically saying we want your positive things, you want good things to be very good, and don't want to have anything for the bad things, right? So for this, if you remember, we discussed the logistic function or the sigmoid function. So says that given some word, so suppose this is my context and this is my word, given some word and context, I want to maximize the probability that their output is they are correlated. That means z is equal to 1 whenever w and c. So I say that z is equal to 1 is that they appear in the positive samples, and z equal to 1 if they appear in the negative samples, then z equal to 0. So if some word and some context is positively occurring sample, we wanted z is equal to 1 for that. Otherwise, we wanted z equal to 0 for that pair. So we want to maximize this probability. Maximize the probability that W and C is in the positive samples if they occur together. If they do not occur together, maximize the probability that they occur they are in the negative samples. And so we can write this as because we have to do this over all the words in the data set. So we just write it as maximize over all such pair probability that it is in the positive pair or the positive set, and deduct over all pairs which are in the negative maximize the probability that they are in the negative set. So why is this fast? Because this each of these probability requires only computing this term, the logistic function, which is basically 1 by 1 e to the power minus say w transpose c, and you just have to take a product of this instead of this where you have to compute this w word into h of each j and then take the sum of this. So this is much faster than that. So this negative concept of negative sampling is clear, right? How it helps to speed up your process. Okay. So is there any doubt? Okay, so the second technique that was discussed was contrastive estimation. So contrastive estimation basically says that we have two sentences. One is eat banana and monkey is say what it is, cars. So we know that this is a positive sentence and this is a negative sentence, and somehow we want to give a score for each of these sentences. So given a context, say set eat, given a context eat, I want to predict bananas, and then suppose given this eat and bananas, we wanted these two words occur together, and we want these to have some high score, and the probability that eat and cars occur together, or we want uh, this score to be small. Right? We want S to be high because that is a positive thing, right? We always increase whatever positive thing we have, and we have if we have anything which is negative, we want that to be as small as possible. And let's start to be small. So now our training basically becomes we want to maximize this S minus XR. We want to maximize this difference. So in the sense you have S here, and you have some SR here, and you want to say that this is very large or large by some quantity, say M. So once we have this, once we train our network, so we train this model. Once we train it and get a loss such that this condition is satisfied, we just stop and say that okay, whatever parameters we have learned till now, those will be that will be uh, taken for the word vectors that we have. Any doubts till now? So these techniques are a bit
No.
okay. So actually these techniques are a bit complicated. It's not possible to explain everything in a few minutes. So I just gave a brief idea. If you want, you can. I think does taught well in the lectures, or you can just look at some YouTube videos that are for each of these techniques. And another thing that was discussed was the hierarchical softmax. So we know softmax, right? Softmax gives us a distribution over all the possible words in the vocabulary that we have. Hierarchical softmax sort of builds a hierarchy. So suppose you have this p number of mod p number of words. So now we contain a binary tree. So you have this three words. So you complete a tree here, construct a tree. So it will have something like it, and then it will have some root node here. This. So since there are p number of nodes, can anyone say what is the number of nodes, length of the path from the root node to say this node? What is the height of the tree? this is log m, log v, right? Because you have p nodes, you need log p number of, or it should follow a path of length log p to come from the root to the leaf of the tree. So once we, so how is this help? So for each of these nodes, we say that it represents some context, and we have, so this node represents the context of some word, say the context representation. This node will represent the context of another word. This will have another word, and so whenever we are trying to predict, so we have the neural network below this. We have this output layer, we have some hidden layer, and you have the input layer here. This is your X. So given some context, say my context is eat, we have some representation of eat here, and then you have, say this is the you want this to be bananas, you want this to be one. So this is a product of these things. This so whichever node you get from coming from the root to the leaf. So how can you get here? From here you take left, then right, and then right. So by convention they say that if you go left, you are marked as 1. If you go right, you are marked as 0. So using this path from root to leaf, we basically compute the probability that given some word, uh, probability of getting a word given some context we see is a product over all of the probabilities or product of all of the scores that we encounter along this path. And then we uh, uh, so that gives us three techniques for which we can use instead of calculating the denominator of the softmax term. So the main issue that we had here was computing this sum and the denominator, which are a lot of terms. So these are three sub techniques that can substitute that computation. So any questions on that?
So hierarchical softmax is computationally less expensive.
Yes, because we don't have to look at the sum of all these v terms. We just have to look at the products of only the terms which appear in this tree, right? So suppose we have v equal to say 1024. So if you are doing a softmax here, so this will be a sum. You have to sum this say 1024 times, right? And each of these sum will have some computation here, which can be very large. So, but now here we will only look at log p number of things, log p number of contexts. So log of this is basically 10. So you just need to do a product overall only of only 10 of these contexts instead of this 1024 entries that you have. Is that clear? Any doubts on that?
No, thank you.
So another type of representation that was covered was uh, in globe representations. So Flow representations. So globe basically, so earlier we looked at this SVD type methods, right? Where we compute the co-occurrence matrix, then we compute the PPMI matrix, and then we do an SVD. And using this SVD, we uh, get the word representations. So when we're looking at this co-occurrence matrix, we are just looking at the counts that how many times certain words appear together, how many times, uh, what is the score or what is the similarity of these terms with each other, right? Then we looked at this word to back embeddings or continuous back of words embeddings, where instead of looking at the counts, we just said that, okay, this is my context and this is my label. Using this context and label, I want to learn the representation of the word. Here we are not looking at any counts. We're just using the context and the label and trying to learn what is the representation of this, of each word. So now this globe representation, it combines both of these. It combines the counts that we have of the words and uses these learning based methods that we discussed. So then it so suppose we are looking at some probability that word J of appears given I. So it will look at this X matrix that we had, the co-occurrence matrix, how many times I and J occurs together, divided by summation Xij. So that means how many times J occurs overall. So that is this by how many times this occurs. So we're just looking at the probability of certain word occurring together. Just that's it. That's out of all the possible occurrences. So now when we have this, we wanted that the similarity of two words should be similar if they are same, right? Like we wanted the similarity of dogs and cats to be higher because they are similar type of words. So then suppose we have some word pi, we want this quantity to be high. And suppose we define this to be log of this co-occurrence that we have, right? So we have a bit of some algebra and we can show that this comes out to be, or rather we have pi pj. Again, we'll also have pj with pi, similarity of pj with pi, and we'll have probability of I given j. So now if we sum this up together, we get something like pi transpose vj is equal to some terms like this. So these are just some basic algebra. So let's just say that we do not know what these total counts are, because then again that amounts to looking over a whole data set. Let's just say that this is some quantity bi and this is some quantity bj, and then we can write it as pi transpose vj plus bi plus j equal to log of xij. Now we know log of xij, and using this log of xij, we want to learn pi, we want to learn pj, we want to learn bi, we want to learn pj. And once we have this, so finally using this, we want to our objective becomes that these two should be close together. So once these things are close together, we'll get some phi, we'll get some pj, and we can use these as word embeddings for words phi and words I and j. So these are word embeddings we learn for words win wj. So these are your glove embeddings. So yeah, these are the different representation techniques that were covered in the class. If you have any doubts, we can discuss it now. So yeah, any more questions regarding this or previous lectures? First page to the next page. Okay. So this is the last page. This is the first page. So again, this will be shared in that uh, link that is shared in the Excel sheet. You can also access it there.
Can you also explain the relation between STD and word to vector?
Oh, okay, okay, that, okay. Hmm. So in word to vec, we saw that hmm, in word to vec, we saw that this first part where we are given the input and we get to this hidden representation. So these weight matrices are said to be of W context. And when we're going from the hidden representation to the output, these weight matrices are said to be the representation that we learn of the words. So we looked at when we looked at SVD, it was something similar, right? Uh, so when we're looking at the uh, so given X, we had this U sigma V transpose, and is this U sigma was the representation. So this is your W word, and this is your W context that we had. So uh, it will be not be possible to show this, but basically it was shown in one of the older papers that whenever you're doing word to vec and you uh, get some weight matrix, say uh, this whole weight matrix is say something called W. So you can just write W as product of two matrices A and B. So this W is weight matrix of all of the parameters that you have in the model. So you can write this as product of two matrices A and B, where A is of this shape and B is of this shape, right? So you can just substitute it and say that A represents your context and B represents your word representations. So which is similar to what we have during SVT, right? So X is basically W word times W context. So you see the relation. So you can also write it as word times. So I can also write this as word times context. So doing a SVD, it amounts to writing X as a product of two matrices, W word and W context. Doing a word to vec is also same as writing it as a product of two matrices. So that means SVD and word to vec does something similar in that sense. So that is what is meant. What they showed, that the relation between SVD and word to vec. Is this clear?
Can you explain matrix factorization?
Oh, matrix factorization is basically so looking at numbers. So whenever if I give you a number, say 6, you can write it as 2 into 3, right? That is, it has two factors. So similarly, you can also given any matrix, not any matrix, but most matrix, given some matrix A, you can write it as a product of two matrices X and Y. So one example that you already know is SVT, right? So you can write A as U sigma V transpose, which is basically SVT. So now we are just factorizing this into three matrices. So you can also combine the first two and say we have say XV transpose, where X is equal to U sigma. So this is matrix factorization. You're just writing that matrix as a product of two different matrices. Is that clear?
Yes, thank you.
Yes, these notes will be uploaded in the Google Sheet that has been shared. So there you will find the link to the uh, drive. You can access this here. I'll upload it after the end of this session. Yeah, if you have no more questions, then you may leave. Thank you for attending. Okay, we'll meet again next week.
So this semantic relatedness, synonym detection, and analogy, like they are not used actually.
Okay, okay. So those are actually used for evaluating how good your representation is. So like
Uh,
we were
Good
looking at
means like the output of all the algos we have discussed.
uh, good means because we assume that uh, representation for dog and cat should be similar, right? Because those are same type of things. So that means in this case we would want something like semantic relatedness. So the dot. So we wanted this, right? Yeah, we wanted this quantity to be high. Thus, similarity of dog and cat to be high because they are similar words and we want their similarity to be high. So it is just a way of evaluating that whether the representations that we have learned are they good or not. So we take the representations from W word, whether from word to back or from the SVT based model or from Clove, and then we check the dot product of those two words. And if it is high, we are satisfied that it is close to one, then we say that the representations that have been learned are good representations. So another way of evaluating is synonym detection.
All these things that we discussed today, the basic purpose was to find a relation or representation between a word and the context.
Actually, given a word, we want to learn a good representation of the word. The main aim was to learn a good representation of the word because a neural network will not take your word as an input. It will take a vector as an input. So we were trying to look
Okay.
at ways to get a vector representation of word. And these vector representations should have the added property that similar words should be close to each other. These similar words should be far away from each other. So that was the whole purpose of all of these techniques that we discussed.
Okay, and then the techniques like to evaluate which technique was doing better, we have these criteria of semantic
Yeah,
relatedness, analogy. Okay,
yeah, right, correct.
okay, yeah. Thank you.
Okay, thank you. Yeah, sure. I'll upload the PPT.